Hello, today we're looking at integrating or getting the antiderivatives of exponential and trigonometric functions. And as always, we're on page 26 in our log tables anytime we see anything to do with integration. So the first thing we're going to have a look at is the integration of exponentials. If we go to our log tables, it's a very straightforward rule for both of these type of situations. If we have e to the power of 5x, if we think back to when we would have been getting the derivative of that, e to the power of 5x would have ended up being 5e to the power of 5x. And the antiderivative, effectively this is the chain rule by the back door, but you don't explicitly do the chain rule, you're just supposed to know this. Or in the exponential case, they actually give you the rule. Instead of multiplying by 5, in this case you would divide by 5. So you end up with e to the power of 5x divided by 5 instead of multiplying by 5 like you would have with the derivative. And as always, what do we need to add on at the end? A constant, because we could have lost the constant. If this was dy dx, we could have lost a constant in our original y. And if we go to our rules, several rules down, we have 3 to the power of x, and when we get the integral of that, it just gives you the rule in the log tables. You have the exponential doesn't change, but we divide by the natural log of log of 3, and again we add on our constant. Now, the reasoning for this you can derive using the log rules that you know, or by rearranging integral or derivatives, but for most purposes you just use your rule in the log tables and that will get you what you need. And always remember to add on your constant of integration. Now, the rule that we have here, where we ended up dividing by 5 instead of multiplying by 5 like we did with the derivatives, is what comes in when we have sine or cosine functions that are integrated. So sine of 3x, if we were doing that in differentiation, we would get the derivative of the sine function, which is the cosine function, and then we would multiply by 3. We would multiply by the derivative of what is inside the bracket. Now this is going to effectively be the reverse of it. And in your log tables, for whatever reason, they have not explicitly written down this rule. They've written it for the exponentials, but they didn't bother writing it down for sine, cos, and tan. So you need to know this bit by heart. You're effectively going to do the chain rule, but you're going to be dividing by 3 instead of multiplying by 3. And this is just an odd bit of memory work that they decided to leave in the course. No particularly clear reason why. I'm just going to take this opportunity to point out to you that just like with differentiation, if we have a constant multiplied in here, it just comes along for the ride. So you could actually write the constant outside of the integral. And for some more advanced questions, it becomes a good idea to be able to recognize that you can take constants outside of the integral. It makes it neater and easier to see what's going on inside the integral, the part that you're actually doing the integration for. So constants that are multiplied, so coefficients of our functions, can get taken out of the integral. It doesn't have any effect whether you have the 4 in here or outside here, but sometimes it can make things neater, and sometimes you'll see it in the exam. So that's something you're able to do. It has no effect, because you're just going to get the integral and multiply by 4 anyway. Now, let's use our rules on page 26 combined with the fact that we know we have this kind of reverse chain rule business going on. So we're going to get the integral, and the integral of sine is going to be minus cosine 3x. And if we were doing differentiation, we'd step inside the function and get the derivative and multiply by 3. When we're doing integration, we kind of do the inverse of that. We end up dividing by 3, effectively dividing by the derivative of what's in here. The reason for that we do not go into. I know that's not a wonderful answer, but it isn't on the course, so we're not going to spend time on it. You are free to look it up, but we will not spend time with it in class. So when we tidy that up a little bit, we end up with minus 4 cos of 3x all over 3, always plus our constant. So this is an important thing to remember. We have to combine our rules on page 26 with the fact that if we're kind of doing the opposite of our differentiation chain rule when we have functions within functions like this. They don't tend to make them more complicated than this. Now, something that is a little bit more complicated is a question like we've got here. And this is another oddity from when they wrote the new course. There is to get the derivative of like a product of terms, you would use integration by parts, but they removed integration by parts from the course. You're free to look it up, and you can use integration by parts in these questions on the exam, and they must give you marks for it. But I'm going to show you the way that they're expecting you to do it in the exam, based on the fact that you're not supposed to know about integration by parts. So if they give you a integral like this, there will be a preceding part to the question where they will get you to get dy dx, the derivative of some other function. And we're going to see how we can use the derivative of this function to help us find the integral of this function. So let's play it through and we'll see what we're going with. So we have y is equal to u3x cos of 2x, and we're asked in part 1 to find the derivative. So this is going to be my u, and this is going to be my v, and I have a product. So I'm going to use my product rule to get the derivative. So we're back to differentiation again. We'll swap between the two quite regularly in integration type questions. So dy dx is going to be equal to u dv dx plus v du dx. And we need to know what u is equal to and what v is equal to. So we have u is equal to 3x, v is equal to cos 2x, du dx is equal to 3, dv dx is equal to cos goes to sine. Where do I go? Yeah, cos goes to sine. Pardon, cos goes to minus sine. Minus sine 2x. And then step inside the function and get the derivative of 2x, and it's just 2. And that simplifies to minus 2 sine 2x. And that is our dv dx. So let's sub in here, and we'll have dy dx is equal to 3x on dv dx plus v du dx. So we end up with minus 6x sine 2x plus 3 cos 2x. Now, hopefully something immediately jumps out at you. Part 2 asks us about the integral of this function here. So when you get a question like this, when you get the derivative of the first function they talked to you about, part of your answer, or possibly all of your answer, is going to be this function that you were, part of your answer is going to be what you're asked to get the integral of in part 2. And then what we have to think of for part 2 is that the integral of dy dx is equal to y plus c. Sort of you get the integral of that plus c, or y would be equal to the integral of that plus c. Probably a better way of putting that. Anyway, the point is we are able to use this fact. We have dy dx, and we're going to get dy dx of this is going to be equal to, we're going to get the derivative of this and set it equal to our original function plus some constant. So the integral of our dy dx is going to be integral of minus 6x sine 2x plus 3 cos 2x dx, and that's equal to our original y, 3x cos of 2x plus some constant. The constant could also be added on this side. It doesn't really make any difference. Now, we can integrate these things individually. We can't integrate this because it's a product and we don't have a product rule. So what we end up with is minus, we can take the minus outside here, and it's minus 6x sine 2x dx plus the integral of this piece here. Now we do know how to get the integral of this, plus 3 integral of cos 2x. We know how to get the integral of cos 2x is equal to this business here. So we end up with minus integral of 6x sine 2x dx plus 3 on integral of cosine is sine 2x, and then we do our reverse chain rule type business where we end up dividing by 2, and that's equal to our right hand side. So we are going to move things around to have our 6 sine x by itself. So we're going to subtract minus 3 over 2 sine 2x from both sides. And we end up with, and change the sign as well. So when you do your rearranging, you will end up with the integral of 6x sine 2x is going to be equal to, I have space, so I'll put it in as a separate line, minus 3 over 2 sine 2x plus 3x cos 2x plus c. Multiply both sides by minus 1 to change our signs to get what we want by itself. And we end up with the integral of 6x sine x to x dx, so it should be a dx in here, is equal to 3 over 2 sine 2x minus 3x cos 2x minus c. So what we have done is we've been asked to get the derivative of a function, and then in part 2 you're asked to get the integral of another function. You'll find that you're asked to get the integral of something that was involved in dy dx of part 1. So you're going to get the integral of dy dx is equal to the original function plus some constant, or the original function n is equal to dy dx, integral of dy dx plus c if you prefer. And then you are going to isolate the thing you are asked for the integral of. So it's a little bit messy, but it is perfectly workable. You're just having to spot that you have a common term here for your part 2. And that is what we need for integrating